Welcome. This is going to be a fun presentation. You guys are in for a real treat. I'm not biased by any means. I'm Kit Cassingham. Welcome to Speaker's Corner. Tonight we're going to read about, or hear about, the Cassini mission to Saturn. And Randy has a little bit of involvement with it. He was a lucky young man. His dad loved anything related to space. And he made sure his kids were front row watching every space mission there was. And then Randy landed the perfect job at NASA's Jet Propulsion Lab. So he got to be even front row for this stuff. I'm not going to give away his talk, but I'm going to encourage him to come up and start talking. So help me welcome Randy Cassingham for tonight's talk.
All right, can everybody hear me all right? Excellent. So, one of the reasons it says artist rendering down here in the corner is this picture is impossible. Because first of all, there was nothing up there to take picture of the spacecraft. It was the one that was taking the pictures. But the other thing is, there's this little golden dome on the bottom here. When it was in orbit, that wasn't there. You'll be seeing this again later, but I will not give you a bottle of wine if you call out that you see it. In my last talk about emergency medical services, I mentioned that I took a little time out for a different career. I said I was amazingly lucky to land a job at NASA's Jet Propulsion Laboratory in Pasadena, California. I know, wasn't that cute? Look at that hair. JPL is the NASA center responsible for sending robotic probes to other planets. And I said my next talk would be about the probe to Saturn, and here we are. But I'm not really going to talk about what Cassini, the spacecraft, did, amazing as it was, since you can go to websites and get more details than I could possibly present in 45 minutes. Rather, I want to talk about what I found personally interesting from the point of view of a space geek who worked at JPL but didn't work on this spacecraft. Because to me, it was about being a witness to the amazing intellect of humanity. We squabble about the most inconsequential things, do you think? Yet, we can do that. We can get a close-up view of the most amazing things. This is a full-width photo Cassini took of Saturn when it was on the far side, so it's essentially backlit. And at the end, I'll show you the last photo of this type that it took. And this is just one tiny sliver of the accomplishment of human ingenuity, and it goes way back. Christian Huygens was a Dutch mathematician and astronomer who figured out what this weird structure was around Saturn, which had been observed by Galileo in 1610, but he couldn't grasp what this was. Huygens explained that Saturn's odd shape was due to a thin, flat ring, nowhere touching and inclined to the ecliptic. And that was in 1655, a ring singular that didn't touch the sphere. And he was right, mostly. He also discovered the first moon around Saturn, Titan, not surprisingly the largest moon of Saturn. And here's why it was so hard to figure out. Because we can't change slides. Hello. Oh, come on. Rick had this problem too. There it goes. So, as small as this little animation is, you'll get the idea. This is what we see of Saturn from Earth with a small telescope, a much better telescope than Huygens had. As we and Saturn move around the sun, this is what Saturn looks like over time from pretty wide gaps, so you can really see the rings, to the thin, straight-on rings. Now consider that from start to finish, this process that goes by in a couple of seconds takes 29 and a half years. Cassini, the spacecraft, was named for the Italian astronomer Giovanni Domenico Cassini, who was born in 1625, and he's known for discovering 4 moons around Saturn. And he also found that there was a weird gap in Saturn's ring, making it really 2 rings, with the gap in between still known today as the Cassini division. So let's get some better detail, not back to where I started with Cassini's spacecraft photo, but to what we had when Cassini was launched, what the Voyager 1 spacecraft saw in 1980 when it zoomed by. That's stunning for its time, but let me go back to what the Cassini spacecraft saw, which would have made Cassini the astronomer weep, because we can really see his gap and a lot more complexity in the rings. Cassini was the 4th spacecraft to visit Saturn, but the first designed to go into orbit and stay there for a prolonged study of the planet, its rings, and its ever-growing roster of moons. I started at JPL in 1986. The Cassini mission was funded in 1989 for launch in 1997, and by then, much of the design work was done. So yes, it would take about 8 years just to build the spacecraft, integrate third-party instruments, mate it with a launch rocket, and get it on the way. And I am a slide ahead, I think. But I want to back up and say what I mean by an ever-growing roster of moons. As I said, Huygens found the first one. Cassini, the astronomer, found 4. By the time Voyager 1 launched, we knew of 11 moons around Saturn. Voyager 1 helped a lot. It found 3 more, and since it brought so much focus onto Saturn, ground observers found 3 more that same year, and Voyager was able to confirm those. But the finds kept on coming. Before the Cassini spacecraft got in on the act, the moon count was 31, and that's the boggling number I knew as an employee. Care to guess how many we know about now?
56.
And by 56 is a good guess. And by know of, I mean they have confirmed orbits, but not including any really tiny moonlets embedded within the rings unless they stand out in some way. The number is 146, more than any other known planet. And it's not that Cassini, the spacecraft, found scores of moons, but rather the data it collected allowed analysis by third parties to understand that some structure of the rings would only be possible if there was a moon of, say, mass Y in position Z, and by combing through the data sent back by Cassini, they could confirm it. One of the very cool things about JPL is that very often we build our own space probes, the alternative being having big aerospace contractors build it. Even if JPL builds the main spacecraft, others will build instruments or other components. And that's when we get to this slide. For instance, this is just one of Cassini's instrument packages, the ultraviolet imaging spectrograph. There are a lot of Coloradans among the residents, including myself, and they probably recognize the logo in there. The University of Colorado at Boulder. It's Buffalo, and they have a very strong science program. And they built this instrument for Cassini. And one of the cool things about working at JPL is we all had access to the viewing gallery overlooking the floor of the spacecraft assembly facility, a giant clean room, which was next door to the building where I worked. So I'd sometimes go there during my lunch hour just to see them work on building the spacecraft. Usually I was the only one in the gallery, and sometimes the only one there at all, since the workers were often at lunch too. But I loved seeing the progress made between the visits. What I want you to take from the next photo is the scale. Let me jump ahead to the nearly finished spacecraft taken by someone inside the clean room. Notice the guy standing next to it. The spacecraft was 6.8 meters high, 4 meters wide, or 22 by 13 feet. It held 12 science instruments, not just the obvious cameras, but a magnetometer to measure magnetic fields, imaging radar, multiple kinds of spectrometers to learn the compositions of things like plasma, Saturn's rings, ions, a cosmic dust analyzer, and then a lot more. All together with fuel that weighed 5,600 kilograms, or 12,300 pounds, more than 6 tons, bigger and heavier than a fully loaded commercial delivery van. And that van was launched on October 15, 1997, about 15 months after I left JPL to work full-time as a writer and publisher. Saturn, depending on where it is in its orbit, is about 1.2 to 1.7 billion kilometers away from Earth, or about 3/4 to a little over 1 billion miles. The neat thing is, to get there, they didn't point the rocket at Saturn. Instead, they pointed it at Venus, pretty much in the exact wrong direction. Why? Not because the men on the team were afraid to ask for directions. Rather, it was because Cassini was so big and so heavy, we didn't have a big enough rocket to get it to Saturn directly. By looping around Venus, they could get a gravity slingshot effect, a boost to get it up to a higher speed so it could get all the way there. Okay, it's more complicated than that. After its launch on October 15th and its Venus flyby on April 26th of that year, Cassini looped around and got a second gravity assist from Venus on June 24th of the year after that. Then 2 months later, it zoomed by Earth and got a third boost. So, let's see. This is the orbit of the Earth, and this is our launch, and it came around. It's kind of hard doing this sideways. It came around this way, went by Venus, and then came around again. And I can't quite actually see it from here, but Venus, Earth, and then by Jupiter, and then finally to Saturn. And when it went by Earth, it skimmed by at only 720 miles above Earth's surface. 720 miles is well inside the orbit of communications satellites. So after flying for almost 2 years, more than 1 billion miles, it was 720 miles away from Earth. But by now, it was going really fast. By using these gravity boosts, it didn't just get there, but by not using its fuel to get speed, it could reserve that fuel so it could move around Saturn and its moons to collect the most science data possible once it got there. And by the way, yes, a planet's gravity can also be used to slow a spacecraft down when it arrives, so it doesn't just go shooting by. And here's what it's found. I chose this photo from 2011 for two main reasons. One is so you can grasp just how thin Saturn's rings really are, yet so substantial that look at the shadow they cast, since the sun is shining slightly from above the ring plane. And second, what's that on the upper half of Saturn? A storm. I want you to contemplate the size of that storm, which is hard because you don't have anything to compare it to. So let's imagine that Earth is right next to Saturn. How big would Earth be in comparison? So let me add it and put it in as a full disk, not side-lit like Saturn, so you can really see the difference. Earth is that big. And Saturn isn't our biggest planet. Jupiter is. So here's what I find totally mind-boggling about all this gravity assist trajectory business. First, that some brilliant person figured out that if you get the math right, you can use a planet's gravity to pull a spacecraft to speed it up, yet just miss crashing into it by just the right distance and go flinging out the other side after stealing some of that planet's energy. And that's just the barest start, because you can't just point a spacecraft at any old planet and figure it's going to get flung out in the direction you want it to go. You first have to figure out where the planets are going to be when the spacecraft gets there and aim the spacecraft exactly correctly so that the planet's gravity will pull it in, thereby speeding it up to the right direction rather than pull it in and pound it into the surface and making a big crater. And you have to know precisely not just what direction it will go, but at what speed when it's flung out the other side. So pause for a moment to consider the thinking involved behind that. And remember that all the planets aren't just sitting there. They're all in orbit around the sun. They're moving targets. And we have to figure out how to swing by, get flung out behind that target rather than crashing into it, and zoom into space toward where we know the next target will be years later. And the whole time, as the spacecraft is speeding out toward its destination, in this case Saturn, what's happening? It's slowing down because it's being pulled on by the gigantic gravity, not just of the planet it just passed, but also the gravity of the sun, which is more massive than all the planets combined, which, of course, also has to be taken into account in advance, because that changes when the spacecraft will get to the next destination for the next gravity boost. And here's why you thought high school algebra was hard. Well, at least I did, and that's why I'm a writer and not a scientist. And because it's JPL, of course, they have a chart to show it, starting with the launch. And you probably can't see it because it's kind of tiny, but there's the launch right there, and the speed goes down even though it's broken Earth's gravity. That's the Earth pulling it back as it speeds toward Venus. But the sun takes over pretty quickly because Earth and Venus are relatively close to the sun. That first hump is going by Venus. And I don't even pretend to understand the math of the notch in the top of that. But then the spacecraft fired its rockets again to speed back toward Venus and go by it again, and another notch, and then get a quick boost from Earth. And then it fired its engines again to keep its that's the Jupiter flyby right there. And then it hits the orbit and gets pulled in really fast. And of course, we veer it around so it doesn't crash into the planet. And then it sits there and goes faster and slower as it goes around the planet. I just find that astounding. And it's also astounding to me that years of fascinating data can be condensed into one little chart that shows the whole path to and around Saturn in a fascinating way. And did I say mind-boggling? Because this is what science gets us, more knowledge to move humanity forward. And as we saw, not just with Cassini, but with many other missions, they usually do get there, usually within seconds of what the plans called for. And those plans were all put into place in advance by brilliant men and women, Americans and others, who work together and together understand how all this works, because I sure don't. And why? Not just to get there. Unlike for us, the trip isn't the thing. The spacecraft doesn't just need to get there. It and its scientific instruments have to survive the journey. Its instruments baked by intense heat when it's near the sun, and frozen by the cold of space, 1 billion miles away from the sun. Think about that. Can you put your computer into a standby mode for, 7 years? Then say, wake up, time to do intense work for 13 years? Yeah, mine wouldn't either. Cassini's mission at Saturn started when it went into orbit on July 1, 2004, and I was very privileged to travel back to Pasadena at the end on September 15th, 2017. At that time, its computers still worked. Its radio transmitters and cameras still worked. Its engines still worked. And all those systems and more have been working together to get the photos and the data back to Earth 20 years after launch. And remember, all those parts had to be purchased years before that to be tested, assembled into components, and integrated into the spacecraft. With few exceptions, its parts had been working for 30 years without any possibility that we could send a technician to fix anything that might fail. In other words, the whole mission ran on 1980s technology, and for the most part, it worked perfectly. And here's how we get all that data back. The Deep Space Network, run by JPL to keep track of and communicate with all those spacecraft. I was invited back to JPL a few months before the end of the Cassini mission to learn about their current projects. This dish behind me is 70 meters across, and there are 3 of these antennas in addition to several small ones. A set at Fort Irwin in the California desert, which is where this was taken, and duplicate antennas at Madrid, Spain, and Canberra, Australia, vaguely equally spaced around the world so that at any point in time, there is some antenna that is able to connect with any spacecraft that we've launched that still works. And it all connects back here to JPL's mission control. And there are a few interesting things about this photo, not the least of which I got to bring a friend with me. I don't know if you can see, that's Kit. Right there. And that's the badge she's wearing, and that's her head. So first, even though I worked there, I had never before been in this room. I brought visitors to the viewing gallery overlooking the room because it's so historic and often seen on TV, but it's mostly off limits, even to employees. Second, notice the two different displays showing the antennas. There's one here and another one over here. It's vital to know what the antennas are doing because, did my microphone go out? Or?
Yes.
I can still hear you, though. I can still hear you.
You want mine?
Yeah, let me have yours. This battery might be going dead.
Mission control, we have a problem. Communications has been lost.
Those batteries not lost on Tuesday.
It's a good thing we have an extra spacecraft. All right, am I loud enough or do I need to turn it up a little?
Hold on 1 second. I know what happened. That's a technician.
Well, you can let Kit deal with it. Pay no attention to the man behind the curtain. While he's doing that, oh, that's much louder all of a sudden, yes.
Keep going.
All right.
Okay.
So, we're sitting at mission control where there's really nothing going on that day, but the people at data control, right behind where Kit is standing, they're doing actual work. The antennas are showing what spacecraft are talking to what antenna. And the two green ones are transmitting instructions to the spacecraft. They can tell at a glance what's happening, and if something fails, they see what and where right away. This room is manned at all times because there are missions out there all the time, with the Voyager spacecraft being a couple of the most important and constant. And those main antennas, the ones that are 70 meters in diameter, are fully pointable. And I happened to be on the California antenna while it was moving, and it was amazing how smooth it moved. And they need to be that big to get the amazingly faint signal from the Voyager 1 and 2 spacecraft, which are 13 to 15 billion miles away from us now, which puts them outside our solar system. On that trip, I got to speak to Ed Stone, who was the Voyager project scientist from before it was launched in the 70s, and was still in that role at the time, 40 years later. And I asked him how powerful the transmitter is on Voyager. Around 25 watts, he said. A watt is a watt. We're talking about the power of one light bulb from a bathroom vanity. At least it's a very focused signal by the spacecraft's giant dish, but we're talking a really tiny radio signal from 15 billion miles away. But wait, there's more. Here's that golden dish I pointed out. Cassini was not just the first probe to go into orbit around Saturn to get a long and detailed look at that planet and its moons. It also carried this, Huygens, a lander built by the European Union that was dropped in Titan, Saturn's largest moon, as Cassini approached. Titan is the first moon that Christian Huygens discovered in 1655, so it's rather fitting that the lander be named for him. Titan is so large, it's bigger than the planet Mercury, and it has an atmosphere. And not just an atmosphere, but one so thick that spacecraft can't see through it with anything but a radar. But hey, they can land a probe there for a close-up look around, and Cassini could relay its pictures and measurements of what it found. It could, and it did. So the project planners had to figure out how to do that, too. It was the first time we landed something on a moon other than our own. They thought it would only survive for a maximum of 30 minutes or so after landing, so it was designed to get and relay most of its data on the way down to the surface. But it actually survived on the surface for about an hour and a half and sent more information than even hoped for. So this isn't just another world, it's another world's moon. 4 photos taken as Huygens floated down toward the surface. A couple more amazing things to know. At one point, the controllers at JPL realized they had a good opportunity when Cassini was behind Saturn's rings. Earth would be visible through the gap in the rings, the Cassini division. The controllers had the spacecraft take that picture to show Earth way in the distance in the ring's gap. And when they got it downloaded, they noticed a tiny speck off to the side. I brought it out and lightened it up in hopes you can see it. So here's Earth, and here's a blow-up of it. And you might be able to see a little tiny dot off to the left, and they realized that's our moon. And they didn't think the camera would have enough resolution to see it, but it did. And let me give you another little tidbit to show you just how clever the mission planners were, even on the fly. You've probably heard that Cassini was deliberately flown into Saturn's atmosphere to burn it up. Since the mission launched, they realized that 2 of Saturn's moons, Enceladus and Titan, might have the conditions to host life, at least have what they call prebiotic environments. So in order to avoid the unlikely possibility of Cassini someday colliding with one of those moons, NASA chose to safely dispose of the spacecraft in the atmosphere of Saturn to ensure that Cassini cannot possibly contaminate any habitat or potential life on those moons. Yeah, Cassini was built in a clean room and it's been in space for years, but they can't be absolutely sure the spacecraft is completely, entirely sterile. They don't want there to be any possibility that we could accidentally introduce earthly microbes into those moons by crashing the spacecraft there even 10,000 years from now. So running the spacecraft into Saturn's atmosphere, they could be sure it would be fully incinerated, and that's how they ended the mission. And I went back to California to be there for it. One thing that's very cool about NASA is they truly celebrate their successes, making a little trinket for everyone that works there, even if they didn't participate in a particular mission. When we got rid of nearly everything as we packed up to move to Odyssey, there's one thing I didn't sell, give away, or throw away. And I was going to have it in my pocket tonight, but I forgot to grab it. But I will grab it if you see me tomorrow. If you want to see it close up, you're welcome to ask me for it. But obviously this I kept. But I think the end of the mission might be the best part. In the lead up to Cassini's final day, I sat in on a briefing by Trina Ray, one of the mission science planners who had worked most of her 28-year career on the Cassini mission, and she said that day, still loving it. She noted that when Cassini arrived at Saturn, it had about 2,000 pounds of fuel. As it was doing its last orbits, it had 20, plus or minus 10. The idea was to use the very last of its fuel, keeping the spacecraft stable with its radio antenna pointed at Earth so it could relay as much information as possible in its final minutes before the spacecraft tumbled out of control in Saturn's atmosphere, ending the signal lock when Cassini could no longer point its antenna toward home. After that meeting was over, something occurred to me. They destroyed Cassini so it couldn't possibly hit Titan or Enceladus, perhaps contaminating them, but they landed Huygens on Titan. Wouldn't that contaminate Titan? So I called Trina to ask about it. I caught her on her cell phone and on her way home to try to get some sleep. She said it's a good question, and they anticipated that. Well, of course they did. Here's the answer. If Cassini had crashed into Titan, it was so massive and Titan small enough that it wouldn't have burned up completely, and that's why they figured microbes inside could survive and maybe contaminate the surface. Probes meant to land on a body are sterilized in one of 2 ways, either by alcohol, as in any medical environment, or with heat, as also used in medical environments like baking surgical tools in an autoclave. So Huygens was literally bathed in alcohol, but they also baked it on the way down to Titan. It had a heat shield that kept it from getting burned up in the atmosphere during descent, but that didn't keep it from getting pretty hot. They calculated that it would get hot enough to kill any microbes through and through. And by the way, they had to design all the instruments it carried to survive that heat. Again, thinking not only anticipated problems, but came up with solutions. Cassini's end of mission wasn't just about disposing of the spacecraft. It still performed science right up to the end. Once they decided to destroy it, Trina said in the briefing, they put out word to all the science teams What do you want to do in the last orbits? Orbits that will go inside Saturn's rings, which is to say between the rings and Saturn itself. They wouldn't fly the spacecraft inside the rings before because it was too dangerous. But when it's time to destroy the spacecraft, well, what's dangerous now? They went for broke and came up with new science objectives for those last orbits. The scientists figured out what they could realistically get and how many orbits it would take to get that data. For instance, the magnetometer team wanted 4 orbits. Radio science team wanted 6 orbits, and the antenna had to be pointed at Earth for those, and so on. The total to get everything for all the teams, 36 orbits. The available number of orbits as the fuel was running out, 22. So they sat down and figured out what things could be done at the same time. Could spectroscopy data collection coexist with radio astronomy experiments? And they were able to plan it all out so everyone could get all the data they needed in the time they had. Here's one example that Trina told us about that, again, for me, was mind-boggling. One thing we wanted to learn about all along about Saturn was details about its amazing and beautiful rings to help scientists understand just how they work and how they stay so perfectly formed. To get that understanding, they needed to know their mass, essentially how heavy they are. They tried all sorts of things to get that measurement, especially the thickest ring structure known as the B ring. They tried to see it through it with a camera. When the spacecraft was on one side of the B ring and the bright sun on the other side, they thought they could figure out the mass by how much sunlight was filtered out. They know how bright the sun is, so if they could see, say, 5% of the sunlight coming through, they'd be able to do the math and figure out the ring's mass. The problem? The B ring filtered out 100% of the sunlight, so they couldn't do the math. So they tried the same thing except sending a radio signal between Earth and the spacecraft through the B ring. It's the same idea. What percentage of the radio signal got through? The answer? 0. Again, no way to do the math. But get this, by flying the spacecraft inside the rings, which remember was just too dangerous to do before, they would be able to measure what the gravity pull is from the planet and the gravity pull from the rings. And then they can do the math that lets them figure out the mass of the rings. And that's how sensitive Cassini's instruments are. Even being that close to the gigantic planet and its strong gravity, they were still able to see how much those thin rings were pulling on the spacecraft from the other direction and get a decent measurement of the ring's mass. And that's just astounding. As Trina Ray put it in our conference, there's nothing better for a scientist to say than I don't know. It just means they have more work to do, more to learn. And if they come up with another way, probably a foolproof way to get the ring of the bead, and they did come up with a probably foolproof way to get the mass of the B ring, but I haven't heard what it is. It was because they were destroying the spacecraft that they were able to do something dangerous to get the knowledge they wanted. And that's why I love the contrast between my old job and my new job. I got to work with people. Ooh, dude, that was a pop. I got to work with people like that who had the imagination and creativity to think of this stuff and figure out how to get it done, get the answers they want so they can understand how this universe is put together. And in addition to the scientists thinking about putting technology to work, there are engineers who figure out the parts and the techniques that the scientists use. The exploration that JPL is doing wasn't possible even just 50 years ago when we were going to the moon using a computer whose memory board was a matrix of ferrite beads wrapped by hand with copper wire. That's how they did memory back in those days. They need the geeks, too, to come up with a new technology to do the work. And before we can do this kind of exploration for real, before we had that technology available, there are flights of imagination by another kind of hero of mine, writers. I happen to know science fiction writer David Gerald, who got his big break by selling a script to the first Star Trek series. Even if you weren't a big Star Trek fan, you probably know the episode he wrote, The Trouble with Tribbles. Here's what he said about his job. This is the primary function of science fiction, to be the research and development division of the human species. This literature is the laboratory in which we consider the universe and our place in it. It is the place where we ask, who are we and what is our purpose here? What does it mean to be a human being? If you talk to the scientists and engineers who are making it all happen in real life, most will tell you that their imaginations were initially sparked by science fiction, from the Golden Age novelists to Star Trek, and more recently shows like Babylon 5 and Firefly. Fiction sparks the imagination of the scientists, and their discoveries spark the imaginations of the people creating the fiction. What a wonderful cycle, ever building and refining and moving us all forward under the power of pure thought. And that's why I left NASA to be a full-time writer and publisher. My work explored the gap between thinking and not thinking. On the one hand, I research and write funny stories of people not thinking for the newsletter called This Is True, which has been publishing online every week for more than 30 years. And it's popular because it's funny in addition to being thought-provoking. But I also write about what humans can do with what I call uncommon sense, which is the title of my podcast. Cassini is just one example of that, and this talk is an expanded version of one of my podcast episodes. I have so much fun with my work that since leaving JPL, I've written 45 books, and at any given time, I have at least 2 more in the works. So if you're wondering what I do in that corner office with this special keyboard that enables me to type all day without hurting my hands, it's this. I'm having the time of my life that's so fun, I even walked away from a cool job like that. And I did get out of sequence with the slides, but this last photo, one thing you might notice, there's some little dots of light here and there. So let me point out a couple things. You can see Earth in this picture if you're looking at it on my screen, and this whole picture is 400,000 miles across. And then there's the blink slide, so I'm yammering, and then there's the end. And does anybody remember the question you're supposed to ask?
Could you tell us about those jets on Enceladus?
Oh, yeah, good question. Good question, Rick. I like that. So there's the picture that of Enceladus, and they've got it backlit so they could see this jets of water, because it's got an ocean under there.
What has an ocean?
And this whole ring that you probably have never seen before unless you've seen this specific picture is only visible because we're backlit. The sun is on the other side of Saturn from here. And this is a true color image. And there's Enceladus right there, that little dot. And this whole ring was created by those jets coming out of Enceladus. Doesn't that just blow you away?
Water vapor?
Yeah. Well, basically, it's little ice crystals.
So what kind of ice?
They think water ice is my understanding. And that's basically what all this is made of. It's rock and snow, essentially. And all those little moons that are around, and you saw that one picture, the really close-up one of the tiny gap in the moon, and the moon going in the rings, and the moon going through, and it was disturbing the rings. Those little moons are keepers that keep these rings kind of intact and shaped. And that's why that ring structure exists and persists. And that's just freaking mind-boggling to me. Deborah.
I'm going to be really stupid right now, but I don't understand where the moons are. Are they embedded in the rings?
Are the moons embedded in the rings? A lot of the little ones are, but here's a moon that's just out here. Enceladus is out here, but there are multiple moons like Titan that are not in the rings. The bigger ones are outside the rings, and the little ones are in the rings, and that's part of what's keeping the rings intact.
So it's all encompassed within that circle. Within it's all the moons and everything are encompassed in that swirl.
Are they all in this? All the moons in this world? No, because they don't necessarily orbit in the same exact orbit as the rings. Because, when you look at the rings side on, they're really thin. And some of the moons are up here and down here and over there. Yeah.
So, I guess to follow up on Deborah's question, the larger moons, how coplanar are they with the rings? Because they seem really, really sliver.
Yeah, so she's asking, how much of them are in the ring and how much of them aren't in the ring, and I don't know the answer to that. Because back when I learned about all this, there was 31 moons. So I haven't kept up with all that and know where they all are. Basha? Oh, I'm sorry. Yes. Celia, that's who I'm looking at.
You mentioned other data other than the photographs. What instruments, what other instruments were on board that were bringing back, that were gathering?
What other kinds of instruments? There was a magnetometer, and they're looking at the magnetic fields and how they vary. Do the moons have magnetic fields? There's spectrometers to look at the composition of the various light that they're seeing reflected off the surfaces, because they can then figure out what the surfaces are made out of by what light's reflected. Spectrograms. What else? There's an imaging radar, so they could look through clouds and see the surface and the shapes. They did that a lot on Venus, the Magellan spacecraft. When I was there, it was bringing back just massive amounts of data, because the entirety of Venus is obscured by clouds. So they put an imaging radar on there that they could bounce off the surface, and then the beams would come back at different rates depending on how far they have to go. So a mountain tip would be back sooner, and you could actually, with 3D imaging, reconstruct what the surface looks like. And they actually even did flybys, animations of what it would be like to fly through those mountains, and it was just mind-boggling. John?
What was the power source?
Power source is plutonium-238. So they use radioisotope thermal electric generators, and that was one of the things that we had to fight about. The section I was in at JPL was the systems. In the systems division, we were systems engineering, and we had the people who did the environmental impact reports. So what would happen if, say, as you were launching, and the rocket blew up? And you know what? It has happened before, where a rocket blew up with a spacecraft with an RTG, and what they did was they went into the ocean, found it, brought it back up, put it in another spacecraft, and flew it again. That's how hardy those things are. Yeah, reduce, reuse, recycle, Rick said. Exactly. Any other questions? Yes?
So another techno nerd went to Atomic Energy Commission in 1966. So I remember a lot of the risk assessments you was talking about.
Yes. He worked for the Atomic Energy Commission and knows those risk assessments. Go ahead.
Did the presence of plutonium-238 enter into the question of whether you would crash land Cassini on Saturn?
Did the presence of the plutonium-238 impact the decision to crash into Saturn? And the answer is, I don't know. Probably. But I actually don't know the answer to that question. It's a good question. John again.
I think one of your slides, you had the time for a radio signal to reach Earth.
Yes. That was for Voyager 1 and 2. And that's a really interesting slide, in my opinion. There it is. So Voyager 1 actually flew after Voyager 2. Voyager 2 launched first by, 15 days. And so it's been gone for 47 years, 4 months, 6 days, 5 hours, 12 minutes, and 16 seconds as of when I took this screenshot. if you go to this page on the JPL website, this actually ticks up every second. And all these numbers change. It's really neat. But distance from Earth, 15,490,587,899 miles. 166 astronomical units, which I think is the distance between the Sun and the Earth. Distance from the Sun is very, very similar. And the speed, 38,026 miles per hour. And Voyager 2 is farther away now because it is going faster than Voyager 2 at 34.4-ish. And the reason for that is they had different gravity assists from different planets as they were on their way out.
That bottom line is pretty interesting too. How long it took the light to get to us?
Yeah, and that's actually the thing I was going to point out the most. So radio waves travel at the speed of light. Light is the fastest thing we know of. And if you send a message from Voyager 1, it takes 23 hours and 5 minutes at the speed of light for that signal to get there. And then you reply to it, and it takes 23 hours to get it back to it. So if you ask it a question, what's the status of such and such, it takes 2 days to get the answer. Just mind-boggling to me. Anything else? Yeah.
I just wanted to comment on the question about plutonium-238 as being, that was a heat source, which heat is
Yes.
energy, is power for all of these devices, and 238 is a really low emission, more alpha, and it's not the fissile material that freaks us all out about bombs.
Right.
You can't make bombs out of 238.
Right, you can't make bombs out of 238. You can contaminate things with it, but
Agreed.
Yeah, and her point also was that it's basically a heat source because you can make electricity out of heat. So, and the thing about radioactive material is it decays over time, turns into lead essentially, or other heavy metals. And so the power generation goes down over time, and that's why they are continuing to turn off instruments, particularly on the Voyager spacecraft, because they want to have something to be able to power that transmitter. And at some point, there will not be enough power for that, and we will lose contact. So nobody asked about my shirt.
Einstein.
Well, no wonder you didn't ask. It's a picture of Einstein made to look like a galaxy. And the best part is, it's glow in the dark. And I got this when I was working at JPL from the employee store. So another little trinket that survived. Thanks so much, everybody.
Let's see. Oh, it does work now.
Thank you. I've got more talks up my sleeve if you want them.
It seems pretty popular, Mr. Cassingham.
I try.